30 times by the name inflation. So this is indeed ultra-fast. That is such an extreme light. And so here we find a connection. Now, light at the beginning interacts so busily with matter for the first 400,000 years of the universe, and so it doesn't really travel very far. So the universe was very foggy until it was 400,000 years old, and by then there was light. Now, so this was what we often see, what's called a cosmic microwave background. By now it's redshifted to microwave. At the time, of course, it was very high energy. Now, so these are what we have come to know now about our universe. Just now I was mentioning about breaking news pouring by the day, and this is one example. About 3 months ago in March, we heard a breaking news that, that this experiment named BISAP-2 had a first glimpse of what's called quantum gravity. Now, we all agree that the great revolutions in physics in the last century was Einstein's relativity and the quantum theory. Now, the two do not quite get along when it comes to the issue of gravity. So we've successfully quantized the other three fundamental interactions, and by now accept the theory of gravity, which is still classical. So this is my own biased opinion that the holy grail of physics is the happy marriage, finally, between gravity and quantum theory. So a final theory of quantum gravity is, I think, the duty of our 21st century. Now, what about that breaking news? That was the observation of, just now I mentioned that within an attosecond, the universe stretched for 10 to the 30 times, during which the space-time were so stretched and its quantum effect, if it exists, had some perturbations, fluctuations, which can still propagate without trouble, unlike photons, which during the first 400,000 years were not being able to, preserve its own identities when they collide quite busily. But till the end, when finally the photon separated from ordinary matter and given us this cosmic microwave background, these original quantum perturbation of the space-time or quantum gravity induced during this inflation time made its own fingerprint onto this cosmic microwave background. And that's what this group had observed. Now, in the meantime, we have heard so much wonderful stories today about the tremendous advancements in laser science and technology, for which Gerard has made such decisive and pivotal contributions over the last many decades. This is one of the variants, a different rendition of what's called the Mourou plot. We have just now heard from Adrian, the Schwinger limit, and there was the much talked about chirp house amplification earlier. I agree essentially with every word here except here. Now, there's, by the way, I took this rendition of the Mourou plot from our friend Sergei Bulanov. Now, to me, these two words don't go together. I think the word limit was really antithesis to the word Mourou. So for Gerard, there's no limit. So this is this is an interesting combination. Now, it comes to wonder, what happens if we put these two very exciting frontiers of science together? how much can we learn? So here's kind of a simple Venn diagram about cosmology, which is a cross-section between several traditional fields: astrophysics, particle physics, plasma physics. And out of this intersection, there is an area where the lasers can do much good to our further understanding of the cosmos. So time is limited. I like to share with you a few examples of what we can imagine about using lasers to understand cosmology. One is the origin of ultra-high energy cosmic ray. This is one of the 11 big science questions for the new century put forward by the NRC Turner Committee back about 10 years ago in 2003. So far, we have observed extremely high energy particles on Earth coming from outer space up to as high as 10 to the 20 eV, which is about 10 million times more energetic than the particles accelerated, protons accelerated in the LHC at CERN. And so far, we don't know how and where they were accelerated to such a high energy. So the origin of cosmic accelerator was one of the big problems. And one possibility could be that these ejecta or astrophysical jets, which are mostly in the forms of plasmas, might have been excited with plasma Wakefield, not necessarily by laser or particle beams, because we are not, astrophysical settings may not be able to organize things so coherently, but perhaps by shocks, etc. Now, with the limited time I have, I would just mention this possibility that very high energy cosmic rays may even has to do with laser Wakefield acceleration concept. And to do this, to confirm this, there's a lot of needs in laboratory proofs. Now, the next example would be the study of the celebrated Hawking evaporation of black hole. Now, I would like to say that this quantum gravity that I mentioned a second ago happened at the very beginning of the universe, and we can hardly reproduce that in the laboratory. But there is another very, very important window to look into the crosstalk between general relativity and quantum mechanics, which is through the Hawking effects of black hole. Now, black hole is predicted through Einstein's general relativity. It's a classical solution. However, Hawking, in one stroke, connects Newton's constant, which is, by the way, let me repeat here. This is the celebrated Hawking temperature of black hole. In one stroke, this expression connects the Boltzmann constant here, the Planck's constant here symbolizes the quantum mechanics, and G here is the gravitational acceleration at the event horizon of a black hole, and that involves Newton's constant. So in one stroke, three branches of major branches of physics are connected. And so this is indeed a very, very important window to look into quantum gravity. Now, but the bottom line here is that the astrophysical black hole Hawking effect can hardly be observable. That's mainly because the typical stellar-sized black hole mass is so large, and it's in the denominator, that the Hawking temperature is so low and weak, the evaporation is so weak, and it's hardly observable. And another very important reason for wanting to understand better the Hawking effect is that because of that effect, well, let's first say that imagine there's something involving with information loss. This is currently under tremendous debate among the international community, and that has to do with the following. Imagine you have a computer full of information. You throw that into a black hole. The black hole gets a little fatter, but the Hawking effect is just continuing, and so this black hole, through the Hawking evaporation, is getting thinner. It's losing its mass, turning into a black body evaporation, which carries very little information. So there is the big debate among experts on the nature of this Hawking evaporation. Where did the information go? Quantum mechanics dictates that information cannot be lost. That's what's the so-called unitarity principle. And so if you care and you check newspapers, everything, and there's lots of talk about that. And there's the wonder about whether seemingly innocent black body radiation of the Hawking effect involves entanglement at all. And there's a recent proposal, well, several years by now, by Prochinsky and company, UC Santa Barbara, that perhaps then this black hole isn't entirely Einsteinian. Perhaps this event horizon isn't just an innocent boundary, but it's actually a thin membrane he called firewall that burns off all the information whenever a computer or refrigerator or whatever falls into. And there are other ideas, but it's clear to everybody that this debate does not have a conclusion yet. So let me just quickly say that 40 years after Hawking's discovery, actually this year we celebrate the 40 years of Hawking's seminal discovery, the nature of the black hole evaporation is still under debate. That adds to the importance of further understanding it using laser in the lab. Now, how does that go? A year after Hawking's seminal discovery, Bill Unruh made a study and pointed out that there is a very similar effect happens for an observer undergoing a uniform acceleration. Now, for an observer stationary outside the black hole, it would see this faint glow called Hawking radiation. And comparing to that, a uniformly accelerating observer will see itself embedded in the heat bath with a temperature that goes very similar to this, except with this G replaced by A, where A is the proper acceleration of this observer. Now, so if based on nothing else, just by thinking of equivalence principle, one would hopefully be convinced that instead of studying this black hole Hawking effect directly, which as I commented just now, is near impossible because the physical black hole is just too big. Now, instead, if one can find a means to accelerate a detector violently, as strong as you can possibly imagine, so that just this A can be huge, that you can create in the laboratory a huge temperature, let's call it Unruh temperature, and to study whether it's this temperature, this faint glow of this heat bath indeed is entangled or or something else. So this is the motivation, and so the idea is with the tremendous advancements in laser science and technology, one can hopefully establish such a standing wave or transient wave pattern where, like Adrian just now was commenting, where there are antinodal points that you only have the E field. And if you manage to put a test particle here, let's say electron, then the back reaction of this electron to the heat bath may hopefully kick the heat bath photons back on shelf. And interestingly, in the proper frame of this accelerated electron, this Unruh effect will be isotropic. So boosting back to the left frame, it's in the forward cone. The classical LAMO radiation is that it's a dipole radiation, and boosting back to the left frame has a blind spot right in the middle. So the hope lies in looking into this axis to maximally reduce the conventional photon background to pick out the Unruh signals. Now, so just a few more words about this Unruh effect. Now, Unruh, as I mentioned to you, there's an Unruh temperature. I skipped this Boltzmann constant on the left-hand side, and this alpha is the test particle's acceleration. The E field is divided by its mass. Now, questions remain, tons of questions. Can the electron serve as detector? Does the electron radiate anything at all back in the left frame? And what is the right temperature for this Unruh effect? It's been pointed out by several authors that laser-induced acceleration is non-uniform, and therefore it does not induce a horizon. The horizon, this is a Minkowski spacetime. The world line of an uniformly accelerated electron goes like this. These are the light cones, and the light cones serve as the horizon for this Unruh particle. Now, when an acceleration was not from infinite past to the infinite future, this event horizon actually does not exist. It's like you started from somewhere. Now, nevertheless, one can still define an effective temperature, Unruh temperature, that goes like this. And surely the laser frequency appears. Now, one can see that this whole expression approaches a constant when a bar is much larger than 1. So that simply means physically, when you have an extremely violent acceleration, this line is, though you are not starting from infinite past, it's just per laser cycle, but it approaches the light cone so quickly that it's effectively acting like a uniform acceleration from negative infinity to negative positive infinity. So this tells us that the higher the laser peak power, the better. And I believe that IZES or the ICANN is the way to go. Now, Adrian has already given us a very nice description about the breakdown of the vacuum. So I would just quickly make a few comments. If I did not mention a few, there are tons of work in this area, so I may have missed some very important citations here. I apologize for that. So the one point that I wish to make is the following. It may be just simply semantics, but in my own view, there's a interesting difference between what I call spontaneous versus stimulated pair production. In the case of spontaneous pair production, we're talking about a setup where in the initial condition, there's no particle, no photons, no electron, but just an E field. Now, by raising this E field, you effectively are tilting this Dirac sea. So much so that if your tilt is enough, and this is the good old Schrödinger mechanism, then the pairs can have a chance of tunnel through. And in comparison to that, what I like to call the stimulated pair production is that you have an initial state electron or photon that assists this thing to happen. And so in that case, we have seen experiments. Now, this, in addition to the upsilon that Adrian just mentioned, there's, in addition, since we invoke laser to do this work, there's also what's called the adiabaticity parameter, and that also plays the role. So far, our laser intensity is not yet able to push us over the Schwinger limit, but what's found was that with a few interesting arrangements, we may be benefited by reaching the limit faster. For one thing, instead of setting up your system exactly with a pure E field, imagine yourself having a parallel B field. Then, depending on the strength of the B field versus the E field, there is a chance where you can enhance this pair production yield before you reach the Schwinger limit. Also, the frequency of the laser field also provides a boost. And here, these are the plots for laser frequency that is in the units of electron rest mass. Now, so these are the examples, and so the heavy-duty science part is done. So let me share with you a few photos. And this is where I came from. And here I'd like to mention an interesting parallelism between Gerard and myself, although my science contribution is in no comparison to his. But we have a slightly similar history. We were not born in the US. We came here and spent a major fraction of our career in the US. For that, we certainly appreciate very much. Then, almost around the same time, you went back to France in 2005. I was invited by my alma mater, the National Taiwan University in Taipei, after decades of working at Stanford, to head this new Center for Cosmology and Particle Astrophysics. And so this is our Le Cospa new building, which is under construction currently. Now, in the year 2009, Gerard came to Taipei for a workshop. And so this was, I believe, your first visit to Taiwan. And we had a great time there. You can see the title of his talk. Eli was there. And this is another shot of Gerard's lecture. And so already then, we talked about applying extreme intensity laser to cosmology. And you may recognize some of these people there. Now, more recently, last year, we signed a collaboration MOU on laser cosmology. This was done in the French embassy in Tokyo. I think I put it down wrong. This is November. So it was a tremendous occasion. Yes, it's in November. Now, also last year, I had the tremendous pleasure and honor to be invited by Gerard to his beautiful home, Gerard and Marcel's, and I appreciate that very much. And that beautiful morning is unforgettable. Also, the beautiful apartment that you have. Marcel, this is our photo. I would never forget that beautiful sunlight. So here's to say happy birthday, Gerard. Now, there's a Chinese saying, life begins at 70. So you're newborn. That wasn't the end. Now, so, well, you probably have seen this Disney movie, Buzz Lightyear. A famous quote, to infinity and beyond. Now, this quote from Gerard, I just learned this morning from Janice, I think. So I quickly copied it down. Now, but this is really a prophet. What it says, well, this is back in 1992. So ultrafast science is a tool that can be applied to further the understanding of almost every conceivable scientific discipline. So cosmology is another one. Yeah, thank you for your vision. Yeah. Happy birthday. Thank you. Thank you.
Okay, thank you, good. Here we go. Here we go. Well, thank you very much. I have to say, you know, wow, I did something. Yeah. Thank you. Yeah, I have to say that after all what I heard, I said, Jesus, what I have done. You know, it's incredible. Incredible. Thank you very much for all your very nice comments, you know, and about my contributions, you know. Anyway, and so what I like to do is, in fact, because, of course, 70 years is very special, like the Chinese says, you know, basically it's a rebirth for myself. And so I had to think something very hard. I wanted to really to present, you know, to present this group, you know, something very, very new, novel. So you know, we have been working for some time, you know, on breaking new barriers, new frontiers. And one of the frontiers is, of course, the attosecond, and that we have heard, of course, this fantastic talk by Paul. And what we take really to go into the zeptosecond. And if you go to the zeptosecond, you know, if you have 1 joule in zeptosecond, you have 1 zetawatt. You know, it's easy. 1 joule is very small. An hexawatt is a millijoule in a zeptosecond. So I say, well, maybe we should really try to look in these directions, because trying to build larger and larger systems is expensive and more difficult. So so this is what I said, 70 and plus 70 and zepto and zeta, it's rhyme, okay? So, and my good friend, Toshida Jima, who was supposed to be here, but he just got sick with pneumonia, and unfortunately, he's not with us. So I put his name on this talk, because that's a lot of things that we were tossing around. Here what you have, you have Peter Higgs, the famous Peter Higgs, and you have Towns. And Peter Higgs, in this picture here, is of course a symbol of high energy physics. And Peter Towns is a symbol of laser, of course. So what this slide is supposed to represent is really the unions between laser and fundamental physics. And this is one of the things that I really like to do, And since we started the CPA with basically a few years after we started the CPA with Dana. Now I'm trying to get this thing. Okay. Oh, I have to. Okay, there's no escape. Okay, why don't you do? Yeah, thank you. Okay, so next slide. Yeah. So, and also I was tossing around what kind of title I was going to give you, and one alternative was really, you have seen nothing yet, because I think we have really accomplished a lot, but there is a lot of things to be accomplished. Okay, so why this endless pursuit for peak power and short pulse duration? What about this obsession? Okay, well, because right now, for instance, if you really want to look at fundamental physics, like Adrian showed you, you have to go to SLAC, very, very, very large machines, and they work with particles. Very difficult to accelerate particles, takes a lot of energy and so on. So it would be very nice if we could replace beams of high energy particles with ultra-intense light. So, I mean, there is two ways. You could use high energy or intense light to accelerate particles, and then do the same thing that you can do at CERN or at SLAC, except on a smaller scale. Or maybe use the field itself, if the field is large enough. So anyway, in order to do this thing, you have to have, of course, very large peak power and short pulses. So I'm going to describe a path to zeptosecond and zetawatt. Thank you. Well, so you have seen, of course, this curve. Yeah. So until now, well, until, we'll say, until 1990 or so, basically. I mean, atomic physics, I'm sorry, the high intensity or laser, I would say. Could you go back? No? No, go back. Yes. No, go back to atomic physics, yeah. Anyway, good. I mean, basically, laser has been very, very good since 50 years. It's been very, very good, and have done really some formidable accomplishments, in atomic physics, okay? 1eV physics, okay? Now, if we want to go to the next level, to the nuclear physics, and next level again, trying to particle physics, then you have to, EV is not enough. You are dealing with characteristic energy in MEV or GeV and TeV and maybe PeV, okay? Anyway, so, and if you really want to do that, it's going to take intensities. It's going to take power, laser power in these regimes at 10 to the 18, 10 to the 25. And this, the 10 to the 25, by the way, has been set really, to have protons, relativistic protons and so on. And above that, as we have heard already by Adrien, then you are in domain of vacuum polarizations, in vacuum physics, you look at the structure of vacuums and so on. Fascinating physics. But it takes you, of course, it takes you big power, it takes you field, to do this work. So we have to find a way, right, to go and climb the ladder. So if you really want to get very high peak intensities or short pulses, like Paul said it, maybe in a different way. Anyway, you have this duality between pulse duration and peak intensity. Okay? Usually, well, we say peak intensity, well, or peak power is energy divided by time. You want to have large peak power, make the time short, okay? But, and that's, of course, it's a trivial statement. In order to get high peak power, you have to decrease the pulse duration, okay? But also, the converse is true. In order to get very high, in order to get very short pulses, you need high peak power. And this has been true since the beginning, and with Toshi Tajima, we played with that. We looked, we have this sneaky suspicion that, peak power and short pulses were kind of connected. So we went and we looked at, since the beginning of the laser, okay, 1960s, the free-running laser and then the Q-switching laser and so on. And you look at really the intensities, involved in this, or the peak power involved in this laser. And you plot the pulse durations associated. You find this, basically this straight line. And here you have, okay, as I say, free-running, Q-switching. You have dye mod locking. You have KLM mod locking. You have, you're using molecular modulations and gas harmonics and so on, and even solid harmonics right now. But everything really fits on basically on one line, okay? So the idea is, not yet, yeah? Okay. The idea is very clear from this picture that if you really want to have short pulses, you have to increase the intensities, okay? So how do you do that? This is what we are going to talk about. Oh, by the way, this is also the same plot, if you want, showing laser pulse duration, history of laser pulse duration, and you see that starting from picosecond, using molecular absorptions, Kerlance mod locking, which took you into the 10 femtoseconds and so, and then harmonic generations takes you to the sub-femtosecond regime, attosecond regime. So now the question is, can we go into the zeptosecond? Can we find some trick to do that? Next slide. So what we are going to do, in fact, is we have to find new way to shorten the pulse, okay? And one nice way to do that, if we could, will be to use an ultra-relativistic mirrors. if you use a conventional mirror, and that basically is connected to what Adrien said about boosting the E field, with the gamma factors. But anyway, that's another way to see it. Okay, if you take just a conventional mirrors, and this mirror is moving, at a speed of much less than the speed of light, and you have this pulse coming, this E field coming, bouncing on the mirror. Next slide. What the reflected light, of course, is going to be slightly shifted by the Doppler effect, but it's going to be roughly the same thing. Okay? Now, if you really are acting now, if you find a way to make a relativistic mirror, okay? So you have this mirror now move at something close to C. The light, of course, this incident light goes at C. And next slide. And the reflected light, next one. Yeah, the reflected light will also, just a minute. Yeah, will also move at C, okay? So the reflected light basically is stuck to this mirror, so, and it won't be able to really to move very far, okay? It's going to move far, bien sûr, it's going to be a function of the difference between the C and the velocity of the mirror. But roughly speaking, you see, if V equals C, I mean, the light stays stuck on the mirrors, of course, and all the light which is here, a fraction at least, is being, is going to be compressed by the mirrors. So that's a very elegant way to compress, very efficient way, in fact. And so, next slide. So here we have. So this is, I looked at how we could do that, okay, for some time now. And in fact, okay, next slide. In fact, we started to do that with Natalia Nomova at Michigan. Natalia, she's in the audience here. And by using what we call this lambda cube regime, okay? So now what we have to do, as I said, trying to make this relativistic mirror, okay? So the way we did it, if you are taking the laser pulse, Gaussian beams, that you are focusing, you are going to focus the beam on, and if you do it, you do a good job, you are, with F1 optics, for instance, you are going to all focus this light on the lambda square, okay? Now, if the pulse is very short, if the pulse is, say, one cycle, okay, all the light, all the photon basically will occupy, or the energy will occupy a volume of lambda cube, okay, lambda square times lambda. And now, if you're in a relativistic regime, you have intensity is so large, the pressure of light pressure is so large that, of course, it's going to make a dent. It's going to push the electrons, inward, and the ions, which are much more massive, of course, are going to stay for a short while, put, okay? So, as you say, you are going to, as you can figure, you are going to build this enormous electric field. So, and as we show, and this critical surface here, this is where the critical density is. This, as a critical surface here, you have a mirror, and it will move at the speed close to the speed of light, okay? So we have shown, Natalia showed, that was 10 years ago or so already, that if you had intensity, which is expressed here by this, what we call A naught, okay, this value, which in fact is a normalized ponderomotive potential, A naught is basically a function of the square of intensity. And you have basically, you should be able to, this way, to produce a pulse of durations of 600 attoseconds over A naught. Okay, A naught is equal to 1 for intensity at 10 to the 18. Okay, so let's suppose that you have a laser which has 10 to the 22 here, which means is 10 to the 4 times 10 to the 18, going to be about 100. Okay, so you should have about 6 attoseconds. Okay, and well, I mean, she plotted with, that was done by particle code simulations and so on, and she had quite nice straight line. Okay, so this work was done at the University of Michigan with the lambda cube, but lambda cube was working at the millijoule. In fact, when I thought about the lambda cube, I wanted to be in a relativistic regime, even with millijoule energy, that is at a kilohertz, I wanted to be in this relativistic regime, and that's the reason I wanted, we had this lambda cube. But now we are going to use that to accommodate much, much larger energy. Okay, so now, as I said, this lambda cube was supposed to work with millijoule, okay? Now, in order to get this phenomenal, I want to build this mirror, this relativistic mirror with the velocity as close to c as possible, but in gammas, very, very large gammas, okay? So I need energy. And I have to look at ways to compress large amount of energy on a single cycle. So I came up with a way, okay, to compress the pulse from, say, the Thai-Sapphire, 25 femtoseconds, to a single cycle. And I'm going to show it how to do that. First, you can do that, okay? And of course, pulse compressions has been so far very good because they were using guided optics, okay? Very difficult to use non-guided optics, free propagations, because you have this filamentation problem, okay? So because you have this filamentation problem, you have to stay at a intensity reasonable, which correspond to a B of few only. But anyway, right now, there is this laser, which have been built, these petawatt lasers. And there is one thing which is important with a petawatt laser. They provide you with a very uniform field, okay? Not a Gaussian field, but a uniform. So let's suppose that you take this uniform field now, and you are producing some cell phase modulation into a piece of optics, okay? This optic has to be very thin, and this is where the problem lies. You will see that. So you produce these cell phase modulations in order to broaden, your pulse, in order to have more Fourier components in your pulse, so you can make it shorter. Okay? Here, because you want to have a lot of energy, you are going to have large beams, 10, 20 centimeters large. And in order to get the cell phase modulation really you want, to get the spectrum, to compress the pulse, to get into the femtosecond regime, you have to use very, very thin specimen. So you have to go and find someone who said, hey, could you make me, a piece of optics which is 100 microns in thickness, but it's 20 centimeters in diameters. You know, of course, nobody is going to polish you something like that, okay? And, well, you know, I was stuck to this, you know, with this problem for some years, and when I found by accident, I mean, just came to me like this, I said, well, maybe by using maybe some plastic, you know, I would be able to do it. So, indeed, and we checked that with Sergei Mironov here, who is going to be a co-worker in this work, and that indeed, you know, plastics can be very optically very good, and they can be in any kind of thickness and any kind of size. So if you use this, okay, then you can, from 25 femtosecond pulse, you can get you can get a spectrum, and after compression, and we know how to compress, but that is, we are using here a very common, really standard, basically, chirp mirrors. You can compress it to 5 femtoseconds. And once you have 5 femtoseconds, you do it again into now a new thin piece of optics, new plastic. And then you get into the 2 femtosecond regime, which is for 800 nanometers, is single cycle. So these are really the simulation, but the simulation has been based on the Cetal laser. Can you go back? Just a Cetal laser, you know, which is Thales lasers. Okay. Oh, so this is a footprint of the laser. It's very nice, very uniform. Okay. And so this is the pulse duration. And so with this pulse, you know, we run the cell phase modulations, the compression and all that, and we found this 2 femtoseconds. So it's based on simulations, but based on reality, okay? So you see that the 25 femtoseconds, then the 5 femtoseconds, and here you have the 2 femtoseconds, okay? And I really believe that, you know, it should be really doable, and we are going to do the experiment now. So here I really like this work has been done with Sasha, again, with this group, basically, you know, and a very good student, Sergei Mironov and Ifin Kazanov. So, so now I see that we have our single cycle, very high energy, because we can do this experiment with 100 joules, if we want, okay? So let's take, or 10 joules, 100 joules, doesn't matter. We have solved the problems of the thin film, you know. Okay, so now I'm going to really describe that how we can really get into this regime now that we have the intensity. Okay. Oh, by the way, I went a little bit too fast. Now, so now if I'm sorry, can I go back again? Another one. Yeah. Again. Again. Yeah. Was not. Sorry.
Back again.
Yes. This one. Okay. Sorry for that. So now, let's see. So I am here now, okay? I have my single cycle, you know, 2 femtoseconds, 100 joules, which gives me intensity of 10 to the 25 watt per square centimeter, okay? So now I'm focusing my beam on this plasma, okay? And get a gammas of 10 to the 3. That means gamma of 10 to the 3, that means that you are very close to the speed of light, okay? And a gamma of 10 to the 3, in fact, will correspond to a few zeptoseconds. Okay? So what I like about this technique, of course, stay on this line, of course, is you can get very simply into the zeta watt, something I always thought that it will take absolutely huge, humongously large laser systems, very simply. But in addition of the zeta watt, you get the short pulses, and also you get, in terms of radiations, the reciprocal of the EV, which is, in terms of energy, is NeV. So you have basically a gamma ray laser, okay? And at a zeta watt level, and the duration of zeptoseconds. Okay. So now go back again. Yeah. Well, I left you. Yeah. So go back here. So now, I think in the next few years, okay, we will start to really to undertake this descent, toward, the shorter pulses, toward the kind of zeptosecond limit, okay? So we are not very far, okay, I think. So, yeah. So that's simulations by Natalia Nomova, which is absolutely incredible. That's 1 zeptosecond, okay, you see. That's the Eiffel Tower, but it's not bad.
Not bad at all.
It's not bad, 1 zeptosecond, I say, Natalia, I mean, if that is 100 zeptoseconds, I'm happy.
He's got huge wings, Gerard.
Yes, I know, but 10 zeptoseconds after that, you have no wings, okay? It's completely crazy, completely crazy. Well, this is what you're expecting from me, right? Okay. So just to give you an idea of what the zeptosecond is, zeptosecond is the time, okay, for light to go to a distance between the nucleus and the proton size, okay? So it's extremely short. But you can really imagine what you can do with that. If you have zeptosecond pulses, gamma ray lasers, you can really do nuclear physics, like you cannot believe it. So of course, Eli NP and Victor Zamfir, and Sid Gales, who is the scientific director there, are all excited about that. And certainly this is something that we are going to do with Eli. So I'm very, very happy about that. That could be really a very good applications of Eli NP. So now, okay, in summary, I think like we have femtosecond petawatt, I hope that very soon we will have zeptosecond zetawatt. I call that Z square. I'm driving a Z3, but I couldn't really find it, the other Z. Yeah. So, and as I said, pulse duration zeptosecond, peak power zetawatt. And what's nice is you have a free, free electron laser, compact free electron lasers, but which can go from from X-ray to gamma rays. And now, what is very exciting, of course, is you can do now this novel nonlinear optics, but in vacuum, okay? Because, of course, you have the nonlinear effect, the chi3 of vacuum is 10 to the 20 times less than the chi3 of, say, of water, doesn't matter, okay? And 10 minus 17 of air, something like that. But you have a phenomenal intensity, to play with. And you have a shorter pulses. So, and all this thing goes like N2 over lambda square. So it should be really a piece of cake to do this kind. It's what you wanted to hear, right? So it should be a piece of cake. Can I, to do this type of things in vacuum, okay? And I guess I'm going to stop here. Thank you very much. Yeah, okay. Okay. By the way, I forgot, no, I didn't forget, to really thank you so much, but I was going to do that for at the banquet, okay? All the acknowledgement. Okay, so, yeah, thank you. Yeah.
Well, thank you very much, Gerard. I'm sure next time we meet, we'll have the 0 zeptosecond zeta watt or Z cubed laser. So, okay. Okay, we are running more than an hour late. We still have to have a group photo, this historic moment. So we're going to be meeting in the atrium for the group photo. Then the reception has been moved to 7 o'clock. So at 7 p.m. there'll be a reception also in the atrium towards the other end. Then a banquet. At the banquet we'll hear from Ed Moses and Bob Bayer and Don Harder and Dan Blumenthal. Wayne Knox will be the master of ceremonies. And there will also be a short tribute to our dearly departed Alan Hunt. Then tomorrow is a brunch, and that's going to be in the Michigan League. If you don't know where that is, it's where there was top of the park last night. It's a building just in that square, okay? So brunch tomorrow morning will be in the Michigan League on the second floor in the ballroom. At 9 o'clock. And the MC for that is Mark Nattel, there. So you're all invited to both the banquet and the brunch. I hope you all show up. Okay, so let's file out and have a picture taken.